So just to go over, welcome to this session 3 of the last day of the showcase. Just as a reminder, these presentations will be recorded. Questions are encouraged, so please use your chat room. You can use the Q&A button, or you can just unmute yourself and ask questions that way. Other students can please ask questions to the student presenters. Feel free to do that. And if you are not presenting, just please keep yourself muted, okay? And with us today is Ileana. I'm not going to try to pronounce your last name. I'll let you introduce yourself. She will be moderating this session.
Thank you very much, Evie. Just to make sure that everybody hears me. Yes?
Yes.
Okay, very good. So we can start with the first presentation. First, thank you very much for being everybody here today and for joining us. And before starting, I'm Juliana Popescu. I'm also a mentor for the undergrad research for the undergraduate students. I have pre-med students, and I'm very happy to be here with you today. So we'll hear some very interesting topics about from our students. And we'll start with the first presentation, right, with Courtney Martin. Courtney, are you there?
Yeah, me and Sarah's here. I'll go ahead and share my
screen.
Okay,
go on. Thank you.
Okay, hello everyone. My name is Courtney Martin, and I'll be presenting today with my partner, Sarah Sprigg. For the past 2 years, we have been working alongside our mentor, Dr. David Rogers, in his undergraduate research lab. Our primary area of focus has been on localizing the enzymatic activity of the insulin-degrading enzyme, or IDE. So today, we would like to tell you a little bit more about what we've been working on. As I previously mentioned, the purpose of our research is to determine where the degradation activity of IDE is localized. And we're interested in understanding this mechanism because knowing where this event takes place can implicate a possible therapeutic approach to Alzheimer's disease and/or type 2 diabetes.
So one of the main characteristics of Alzheimer's disease are amyloid beta plaques, which form between neurons and disturb cell function. Thus, we want to know more about the degradation of amyloid beta peptide. On the other hand, type 2 diabetes occurs in individuals with an insulin deficiency. Therefore, we're interested in understanding how IDE regulates insulin levels in the cell. We know that IDE, a zinc metalloendopeptidase, degrades both insulin and amyloid peptide, but where this event takes place is still unknown. In the top left corner of our poster, you can see the endosomal processing of insulin and amyloid beta protein. As you can see, both insulin and amyloid beta peptide utilize receptor-mediated endocytosis to enter the cell, where the vesicles then fuse with endosomes. Once these proteins are degraded, their component parts are exocytosed. However, it is unclear at what point IDE interacts with these proteins. We know a majority of IDE is found in the cytosol of a cell, but research has suggested at least 1% of IDE is found localized to endosomes, which leads us to our hypothesis that IDE binds phosphatidylinosyl phosphate head groups on the outer membrane of endosomes, resulting in IDE localizing to endosomal compartments, where it may degrade insulin and amyloid beta protein. In order to test our hypothesis, we hope to develop an IDE variant with the inability to bind liposomes at the PIP head group while still retaining enzymatic activity, so that eventually we can then use in vivo testing to see whether or not this non-lipid binding variant retain the ability to degrade insulin or amyloid beta peptide. If the results reveal that the proteins were not degraded, this would suggest that IDE binding to endosomes is essential to the degradation of these proteins, which further suggests that IDE's enzymatic activity is localized to endosomal compartments. So we developed 3 IDE variants. For each of these variants, we made 3 mutations to amino acid side chains along the proposed lipid binding site on IDE. As you can see on our poster, we outline the anion binding site and the proposed lipid binding site. This model is how we determine which amino acid side chains to mutate in an attempt to eliminate IDE's binding capability. We were careful to select amino acid side chains that are more exterior in hopes that we would not disturb the activation site on IDE. We then tested the ability of these variants to bind liposomes by allowing them to incubate with the liposomes, followed by a liposome pull-down assay. On our poster, you can see our results from the experiment, where we compare the binding activity of the wild-type IDE and its variants to liposomes without a PIP head group, and liposomes with a PIP head group, which are representative of endosomes. A brighter band indicates more protein, which would mean more protein bound to the liposomes. Thus, if the wild-type IDE and its variants were able to bind the liposomes, a bright band should be seen. In the first row, the results of the wild-type IDE can be seen. There is a much brighter band in the DOPC plus PIP column, which would indicate that IDE preferentially binds PIP head groups, as we had predicted. Therefore, similar results would be seen in the variants if the binding site was unaffected by the mutations. As indicated by the weak bands for both the liposomes with and without PIP head groups, our results suggest that mutant 1 and mutant 2 were unable to bind the liposomes, which tells us these mutated amino acid side chains are essential to liposomal binding of IDE. However, after testing the kinetics of these two mutants, neither one retained full enzymatic activity, which tells us we likely mutated amino acid side chains involved in its activity as well. On the other hand, mutant 3 retained full binding activity with preferential binding to the liposomes with PIP head groups. These results confirm that IDE preferentially binds to PIP and that these mutated amino acid side chains were not essential to liposomal binding. These results ended up being insightful for a few reasons. One concern we had was that IDE would bind to the PIP head groups through a non-specific electrostatic interaction, which would be due to the positively charged amino acids on the exterior of IDE and the negatively charged phosphate groups on the PIP head group. However, because mutant 3 has mutations in 3 of these positively charged amino acid side chains, but still retain binding to PIP, we can assume there is a specific binding of IDE to the liposomes, which further supports that IDE does in fact preferentially bind to PIP head groups on endosomes.
Overall, our results indicate that IDE does preferentially bind PIP head groups, which leads us to believe that IDE may in fact localize to endosomes where it degrades insulin and amyloid beta protein. As of now, we are still hoping to find a mutant with the inability to bind liposomes while still retaining full enzymatic activity so that we can further support this hypothesis. Our results thus far tell us that we are on the right track and are one step closer to solving this mystery. In the future, we hope our research can one day inspire a beneficial treatment for Alzheimer's disease and/or type 2 diabetes. Thank you so much for listening, and we're happy to answer any questions that you have.
Thank you very much for your presentation. So we still have some 4 minutes, I believe. If there are some any questions in the Q&A, I don't see anything right now. We'll just wait a little bit, but I want first to ask you something. If you know that this year we have the centenary of the insulin discovery, because you are talking about insulin. So we have the centenary of the insulin discovery by the researchers in Toronto. Let's see. I'll still wait something.
So I have a quick question. Based on the research that you've done so far and the mutants that you've encountered, I know that you're looking for specifically one that has, a certain set of properties that we haven't found so far. Based on the mutants that you have encountered up to this point, do you have any inclinations as to areas that you'd like to focus on to find those mutants, or is it just kind of like a random search?
I wouldn't say it's random, because we definitely, we have that proposed lipid binding site. So we know kind of what amino acid side chains are going to likely be involved in the binding. And I think through the mutants that we have tested with, these mutants, and we've tested even just single mutations as well. I think each time we do it, it kind of gives us another hint telling us like, okay, like I think that maybe this this could be involved. So, it's definitely not random, but finding the right medium, the right mix of mutations is definitely very challenging, just because that anion binding site, that activation site, they're all very close together. So it's a kind of being very careful, but I think we're definitely getting closer and closer each time, which is good.
Do you have another question?
So I have a question for Courtney and Sarah. So you guys have been working on this for a couple of years. Is that right? You said. Do you plan to continue research? Are either of you graduate? Courtney, you're graduating, right?
Sarah is. I'm not graduating until
Sarah is. Okay. So do you think you'll continue research?
Well, of course, so I'm graduating, so I will not be able to continue research here, unfortunately. But I don't think I'm done with research forever. I do hope to go on to medical school, so I'm sure I'll be involved with research in some degree. I do like it, but Courtney, I don't know about you.
Yeah, I think Sarah and I are pretty much on the same page. We both want to go to medical school, but I still think that in some capacity in the future we would like to do research, however that may look.
Sure. Very nice.
And what was the hardest part of your research?
I think that, definitely the concepts that we're working with here are very, very dense, very complicated, that's for sure. So there's definitely a learning curve getting into it. And then just as far as like the day-to-day, it can be, a little tiring. We're kind of doing a lot of the same stuff. And, unfortunately, we do have to make the liposomes, which is like a very long process. And then you make the liposomes and then you do the experiments and it's like, oh, well, maybe the experiment didn't work out, but that could be because, oh, maybe we didn't make the liposomes properly. There's just a lot of variables that we work with. So I think that just like the day-to-day can be a little bit like frustrating, little frustrations here and there, but it's all worth it.
Okay, good luck for now on. Thank you very much. We'll start with the next presentation. So our next presenter, if he's ready, I think it's Callihan Moraska.
Yes.
Right.
Hi.
Are you ready?
Sorry. Hi,
I'll
everyone.
listen.
Sorry, am I okay to start?
Go on.
Okay. Hi, everyone. My name is Callihan Moraska. I am a junior studying public health and biology here at UK. For the past year, I've had the privilege of working on a research study within the Department of Otolaryngology with my mentors, Ms. Julie Jacobs and Dr. Tina Studs. And today I'm going to talk to you a little bit about how we applied rapid qualitative analysis to our study investigating the impact of COVID-19 on families with children who are deaf and hard of hearing. So in general, evidence-based practices, policies, and programs often don't reach the populations that they are intended to benefit. And this is known as the practice to policy gap. And it's an ongoing problem that the field of dissemination and implementation science is attempting to address. As an emerging field, D&I science is characterized by the study of methods to increase the adoption of these practices and policies so that they can be implemented into medicine, public health, and other related settings. D&I science uses both qualitative and quantitative analysis methods, but qualitative analysis methods have been known to be both complex and time-consuming. So for our study, we decided to implement rapid content analysis, which is an emerging approach that allows us to systematically classify and code data without using data transcription. So our team applied this method to study how COVID-19 has overall impacted families with children during this difficult time. So first, to collect quantitative data, we conducted a survey where we collected data from 132 families across Kentucky. We used clinically validated measures to investigate both family and child well-being, as well as overall experiences within the hearing healthcare community and healthcare services. At the completion of the survey, we identified 20 parents with better or worse health outcomes that were representative of the overall sample, and we conducted semi-structured interviews. As shown in table 1 in the middle column there, we did utilize a wide variety of parents based on income, race, and other various factors. After these interviews, we implemented the rapid content analysis method by listening to interview recordings and then completing an interview summary table by identifying key summary points and especially exemplar quotes. And then we condensed these summary points into an Excel sheet so that we could easily identify themes and determine patterns among these families with children who are deaf or hard of hearing. Moving on to the results section, so far, we've interviewed 15 parents because our study is ongoing. As you can see, we have interviewed mostly females, but again, this was representative of our survey study. And I thought it was interesting that with the child's hearing device, 53% utilized cochlear implants and 40% utilized hearing aids. So getting into more of our qualitative results in our preliminary analysis, the most prominent theme we identified was overall parent familiarity with hearing healthcare services and just how the system works. We noticed that there seemed to be experienced parents and then inexperienced parents. And what I mean by this is that experienced parents usually had multiple children who were deaf or hard of hearing or some kind of professional experience within the hearing healthcare system, such as being teachers or just professionals. And they seem to describe a more proactive approach when securing services for their children during the pandemic. So if you look at the first quote, the first mother had 2 children that were deaf or hard of hearing, and she was very adamant about getting her daughter an appointment, that she reached out to the clinic and asked for one. Versus the third quote, the mother describes a more relaxed approach where she wasn't as worried that her daughter missed an appointment, but that's actually really critical because children's hearing changes a lot and they need to make sure they're getting into those appointments. The next theme that emerged from our results was overall disruption in safety net services. So when schools closed, a lot of these children lost access to speech therapy, interpreters, and just overall interactions with children. And I thought the first quote by a mother with 3 children who are deaf or hard of hearing really hit the nail on the head with saying that this community is a very social community. They need those interactions. So it was really interesting to hear the pattern of parents that noticed that their parents or their children's hearing and language skills tended to decline with COVID-19 and disruption in school. Finally, the last theme I identified was just parents' experiences with telehealth services. There was overall a mixed feeling towards telehealth services, and we noticed that acceptability really was based on age of the child, relationship with the provider, and also the type of service. So as we probably guessed that older children responded better to speech therapy over telehealth services, while younger kids had harder times focusing. And also, as noted by the second quote in that box, if the child had like a rapport built with their therapist, then they were able to successfully transition to telehealth services. So in the future, we plan to finish conducting these 5 interviews with parents and then move on to interviews with administrators and other healthcare providers to identify barriers that they face during the COVID-19 pandemic to get their perspective. And we're also going to conduct a 6-month follow-up survey to notice what downstream effects that these families have experienced, and as well as characteristics of families who are continuing to struggle. And what we plan on doing with this information is disseminating it to policymakers and other healthcare professionals to see how we can better serve this community in the future. So thank you, and I'd be happy to take any questions.
Thank you very much for the presentation. Let's see if we have some questions in the Q&A box. We don't have. We'll still wait for some. I have first a question, maybe. Yes. It's about the methodology that you used. How did you choose these families with the children and with the COVID-19 also?
So we send out surveys through various just healthcare clinics to find them. We also posted on the CCTS website through UK, but they had to be diagnosed with in having access to hearing healthcare services, and they had to be living with their parent or legal guardian more than half of the time for their family to be qualified for the survey.
Okay, thank you. Any other questions? Evie, have something? No.
Yes. So, Callihan, what was the most surprising to you about this research and the results that you came up with?
Yeah, I would say just parent, like I talked a little bit about it, but parent familiarity with hearing healthcare services, because we noticed that a lot of parents who had a lot of experience were had the resources to provide to their children, as well as just being very adamant about getting them to the services that they needed. And they were just more mindful of like what their like the problems that their children would face during the pandemic. And then we also saw some parents struggle with like just understanding with what their children were going through, especially during the pandemic, and they had a hard time communicating with them. So we're hoping that research like this can help better help those parents who are struggling.
Sure. So as a follow-up question, do you plan to continue this research, or are you graduating, or what is your status?
Yes, so I am a junior, so I plan to continue doing this research. And we actually have another study that investigates just how parenting styles and behavioral outcomes among children who are deaf and hard of hearing. And that was put on pause due to COVID, which is when we picked up this study. So we're just now launching that project again. So we'll be finishing this project and then also working on that one as well.
Very nice.
Yes.
Thank you very much.
Thank you.
We'll have the next presenter just to be in time. Okay, so our next presenter is Hope Makumbi, right?
Sorry.
Let's see if she's with us.
Yes, I'm here.
Hope, okay.
Can everyone see me and hear me?
Yes, we do.
Okay, let me
If you're
share
ready.
my screen.
Is there any issue?
I think I got it now.
Okay,
Okay.
let's see. Yeah,
Uh,
we can see it.
Can
Okay.
you expand it, Hope?
yeah.
Yeah, because it's too small.
Let me refresh it.
Can you make that one full screen, maybe?
Yeah, I think it was just should be working now.
Just give it a second. It's download. There you go.
Okay. Hello, everyone. My name is Hope Makumbi. I will be graduating this May with a Bachelor's of Science in Neuroscience. And this year I was a part of Spark, which is a program funded by the CCTS to help underrepresented students participate in health equity research. For my research, I'm trying to elucidate the relationship between maternal education and the development of a child. This research is secondary research got from the secondary research from the 2017 National Survey of Children's Health. And from that survey, 21,599 adults responded to the survey on behalf of the children under their care. 6.87% of the children had a developmental delay. While analyzing this data, I was able to determine the significance maternal education has on the overall well-being of a child. Children born to mothers of education no higher than high school had higher the odds of experiencing a developmental disorder. And I thought that is why I believe this research is really important, because we know that access to education is not equal among all communities. Another thing that I found interesting was how low birth weight impacts, how low birth weight could be a factor to a child experiencing developmental disorders. So low birth rate children had 2.48 times the odds of experiencing a developmental disorder compared to children at normal birth weight. And very low birth rate children had 7.29 the odds of experiencing a developmental disorder. And with this research, there are a lot of factors that are related to low birth weight or experiencing a child experiencing a developmental disorder, like socioeconomic status, resources, past family experiences. So yeah, and I'm still very early in this research. We just did this research like over a year, so I'm still very early in the stages of this research. As for continuing, since I'm graduating this year, I don't think I'll be able to continue this specific research with my same mentor, but hopefully as I carry on to medical school, I'll be able to continue my research in maternal health. And that's it. Does
Thank
anyone
you.
have any questions?
Let's see, it was a bit short, so we don't know if we have questions yet. So we have a question here in the chat, I believe. So let me see. Did you see that you have a question?
When I have the full screen, I can't really see the chat.
Okay. I will read that question, right, for you.
Mhm.
So did you do anything to control for the influence of parents' developmental disorders? For instance, if the parent experienced a disorder that may make them less able to complete a greater extent of education.
Well, the survey, since this was a survey, we couldn't really control that. Like the survey was just based off, if you wanted to answer the survey, then you answered it. We didn't really, from what I read from the National Survey of Children's Health, they didn't really ask about prior experiences. It was just a matter of if you wanted to answer the survey.
Any other question? Not yet. So my question, I have a question for you. Why did you do this research?
I'm really interested in women's health and just how the accessibility to support, when you have a child. I know that it's not always accessible in all communities. And I just thought that me doing this research will help me be better prepared as for when I become a clinician to have more knowledge, especially when I work in those communities.
And your future, you see it how? Yeah, what are you going to do?
Well, I mean, hopefully I'll be able to start a clinic in one of those communities and support, maybe have classes for mothers, incoming mothers in those clinics, and provide support such as maybe help for their children if I have some friends who are pediatricians or something like that. I mean, I don't know yet. I'm it's very far from now, but it's a start for me.
Sure. Well, good luck with that. We still have questions, Evie? I don't see any question in the Q&A right now, not in the chat. Thank you very much. I think we can continue, right?
Yes, absolutely.
Okay.
Nice presentation, Hope.
Thank you.
Thank you. Well, let's see. The next speaker, I think we're going to the nursing topic, right? Yes, it's a topic right here. So next speakers, we'll talk about the sleep practice, okay? So we have two co-presenters. Are you ready? Nadja and Nidhiben. Okay, good, perfect. We listen to you.
All right.
There you go. It's in presentation mode now.
Okay. Are we good to go?
Yes.
All right. So hi everyone, my name is Nidhi Patel.
And I'm Nadja Nelson.
We are undergrad nursing students, and we are also children fellows working on research with Dr. Hartley Feld on global health and infant safe sleep. We started working with her about a year ago, and we were mostly collecting data with her. And then we progressed to interpreting that data and coming up with this project of our own. And the project is based in Ecuador, as her project is based in Ecuador for SIDS mortality rate. And we were trying to see, because previous data has indicated that Ecuador's annual SIDS mortality rate is higher than any South African country around there. And so we're trying to determine if prone and side sleeping position that has contributed to SIDS and globally has anything to do in Ecuador as well.
Right, so our study was designed to determine if the Finnish baby box and safe sleep education plays a role in how mothers put their babies to sleep at night. And so the Finnish baby box was designed in Finland, and it's essentially just a newborn sleeping kit. It's a safe sleeping service for infants. And so it's a starter kit for new parents. It has a cardboard box with the baby sleep in, and it also contains newborn gifts that helps the parents start out, being a parent. Finland is a country that has the lowest rates of SIDS death in the world, and they credit that stat with having the baby box and it being a big part of their culture. So we wanted to see if the box, which is really successful in European countries and in the West, can also have the same success in Ecuador, which is a lower income country. And so Nidhi and I conducted a secondary analysis of the longitudinal study, and we had 16 pregnant and postpartum mothers that were recruited from the Shoulder to Shoulder Clinic in Santo Domingo, Ecuador. This clinic partners with our project, and they provide services to the region and that area. Each woman was interviewed about their safe sleep intentions with their child before they were born and then 1 month afterwards. And they were also given the baby box and then newborn essential gifts and safe sleep education from the American Academy of Pediatrics. As for our results, before education, we found that 4 mothers chose to put their baby in the prone or stomach positioning, 10 chose side positioning, and only 2 chose back sleep to start off with.
All right, this is still you. All right, so after the post-intervention data, it revealed that only in 1 month, it revealed that there were no changes in the number of mothers who used that belly position to begin with. But compared to that, there were about 7 mothers who changed to a side position. So there was a reduction of 7 mothers who used that side position. There was also an increase of 4 mothers who used the back position. And there was also 3 mothers who used more than 1 position in our data. Oops. And so the most common barriers reported were family traditions and environmental considerations and education from local hospital that was promoting the side position as the safest position, when in contrast, it was the back position they were supposed to be promoting. And the facilitator of the back position was the education training that was provided at the beginning of the study. And then what we also learned was that many mothers who changed their positioning also reported learning about that at the educational training. And then the baby box was identified as neither a barrier or facilitator, which was kind of the point of our study. And they also reported that family tradition was one of the main reasons why there was mothers who decided not to change their position. That's the reason they reported it. And the culture and the social context also had a lot to do with Ecuador being a region that likes to promote the supine position in that region. Right. So this was a preliminary study, so we're still collecting our data. We still have data coming in and we're still working on this, but this is what we started off with, and these were our initial findings. We found that sleep education was the primary promoter of safe sleep and using the back positioning, which is what we wanted to promote. But we also found that a lot of the mothers did use their education from their parents and family teachings and also their cultural backgrounds to stick with using side or stomach or prone sleeping. So we just thought that maybe that the cultural differences between Finland and Ecuador maybe contribute to the success of the baby box in Finland and other countries, and maybe not it being not so used much more in Ecuador. In the future, we do want to explore this and maybe see exactly why the baby box wasn't used as much in Ecuador. So we do want to continue that in the fall, but we all want to thank you for coming to our presentation, and Nidhi and I are open for any questions you all may have. Thank you. Thank you.
Thank you, both of you, for your presentation. Let's see, we have any questions?
I've got a question. I know that this is kind of framed in the context of trying to adopt different practices, you know, from areas that have relatively low rates of SIDS. I know it's a relatively small sample size. Did you see any incidents in SIDS within the group that you studied? Or do you have plans to kind of expand this out a little more to see if you can get a larger sample size?
So we did actually have a larger sample size, but because, like we said, due to COVID, we weren't able to actually collect and get all the data in. And like you said, we are exploring to see we can collect more data on the sample size we have as well. But I don't think there was any SIDS reported in the data we have reported on the presentation over here. Right, there wasn't any instances in our presentation, and I don't think there was in the larger sample size that we do have either.
Thank you. Another question? Anybody? So I have a question. It's just about the methods. How did you assess the sleeping rates?
Say that one more time, I'm sorry.
How do you assess the sleeping rates?
Okay, so each mother was questioned with a questionnaire. There was like qualitative and quantitative questions asked. And so it was just a survey they filled out in Spanish. We had to translate those, but we did ask them like how they plan to put the baby to sleep based on like their past children, or if this was their first child, how do they plan to put the baby to sleep? So we just asked them, do they use back, side, or stomach positioning? And then afterwards, at that 1 month point, they were asked the same questions again, and then we were determining what had changed or what has caused that change.
Great, thank you. Any other question? Nope, we don't have any other question. Thank you very much for your presentation. We go ahead with the next presenters. So we have the chemistry topic right now.
Hey,
Wyatt Ringo, right?
Yep.
Okay, perfect.
Let's see, let me get this squared away. Okay.
Yeah, we can see that.
There you go. You see the nice public facing version.
Thank you.
Let's see.
Go on.
Well, good afternoon, I guess, at this point. My name is Wyatt Ringo. I work with Dr. Ahwa in the Department of Chemistry. This presentation will be over novel small molecule inhibitors of ARID4B. ARID4B, also known as AT-rich interactive domain 4B, is a protein that's a part of a chromatin remodeling complex that's been implicated in mediating endocrine resistance in certain types of breast cancer. So you can see here, this is the docking model for ARID4B, and it's split up into 3 main domains: the tutor domain, the ARID domain, and then the chromo domain. Previous work in this research, mostly spearheaded by my graduate assistant that I work with, Samuel Lafori, has developed a novel small molecule inhibitor of ARID4B named ARD150. And you can see the general structure of this inhibitor here, along with its docking model on the larger protein. Though this is a first in its class inhibitor, it exhibits poor potency. So it requires relatively large concentrations to function effectively. And the emphasis of further research into this compound is to find more potent analogs of this inhibitor. The overall process of this project, and a lot of this is lead up to the current project that I've been working on, was looking at in silico modeling, taking ARD-150, this inhibitor, and studying the key interactions of this compound within the larger protein, generating analogs to improve those key interactions, and then redocking and picking the highest scoring out of those in an in silico model. Using this framework, it does not require ab initio in silico modeling for every new compound, and allows us to generate a small set of scaffolds on which we can actually function and synthesize new compounds for further characterization and study. That is this project in its entirety. Is this kind of last box on this general strategy, is actually taking those scaffolds and synthesizing and characterizing those new analogs using retrosynthetic techniques and passing them along for further biological study. The general kind of idea for these biological studies is looking at what we've already done with ARD-150 and replicating that for new proteins. So we can see here, and I'm not going to go into crazy detail because this is, again, kind of preliminary work that's been done by the lab group. But we can see using various cell-based assays like CETSA and others, we can show that the framework does target ARID4B. And likewise, studies in mice have shown that the framework is tolerable at very high concentrations, but further synthetic efforts are mostly focused on improving its potency. So this is where the heart of this project really comes into mind. And it's taking these three scaffolds, which are intentionally obfuscated a little bit as research is ongoing, and we're anticipating to patent this and publish this for future use. But this gives you a good idea of the scaffolds that we're working with. Scaffold 1 is the closest to the original inhibitor, ARD-150, and then 2 and 3 are variations on that we found via in silico studies. So using these scaffolds and a small conserved set of starting materials, varying different additions onto the scaffold in different arrangements, we can use a relatively small pool of materials to generate upwards of 30 different analogs of these compounds. Once we've actually synthesized them, we have to go through and characterize them, make sure that they're pure enough for further use, and make sure that they are what we expected using such techniques as HPLC, mass spectrometry, I can never pronounce that word, and NMR. Looking at the kind of synthetic scheme for these compounds, it's going to vary somewhat from compound to compound, just based on the type and also placement of additions to these scaffolds. But the general idea is to use coupling reagents such as HATU, EDC, and DIC to form activated esters, and likewise using TFFH to form an acid fluoride. And this activated ester, or the fluoride, functions as a good leaving group, which can then undergo an amidation reaction to actually attach the group that we want to see. The easiest of these reactions is when we can attach the same group on both sides of the scaffold, so it's just a nice symmetrical reaction. And the most complicated of these are ones where we'll have to attach one on one side and then deprotect the other, and then make that tail itself and deprotect it and add it onto the scaffold. But the most complicated these gets are going to be 3 to 4 synthetic steps. There's a very heavy emphasis on speed and efficiency in creating these compounds, and anything that requires too many steps or has too low a yield is just not considered. So far, we've already synthesized upwards of 15 analogs of ARD-150, and further synthesis is ongoing and is expected to continue through the summer. Likewise, we've already sent off 6 of these for biological studies, and one of them has already come back as being shown to be more potent than ARD-150, which is a fascinating result to already have. By the end of the summer, we hope to have a library of these 30 compounds that have been synthesized, characterized, and sent for biological study, with the eventual aim of either creating a single drug or a family of drugs to be used in anti-cancer applications for endocrine-resistant breast cancer or other possible medicinal applications. And finally, I'd like to thank my mentor, Dr. Ehwa, also my graduate assistant. I've been working with Samuel Afori, the rest of the Ehwa lab group, and also the NMR team in the Chem Phys building, because they make a lot of what we do possible. Thank you.
Thank you very much, Wyatt. Very nice presentation. Let's see if we have some questions. We're looking in the Q&A and we don't have any for a moment. Just waiting for some questions. I'd like to ask you, how did you start this research? I mean, was your idea or was your mentor idea, or what was your part of this research, saying like that?
This is a continuation of a lot of the research that my graduate assistant, Samuel Afori, has been doing for years now. The specific aspect of this project that I personally was associated with is the actual synthesis and characterization of these compounds. A lot of the previous in silico work was done solely by him and other members of the lab group. But the part that I, actual hands-on in the lab was creating these compounds and then characterizing them, and then we send them off for further biological study.
So it means that you collaborate, okay, with other labs.
Yes, yeah, this is it's a collaborative effort for sure. But yeah, it's really interesting stuff.
Well, good luck. Let's see.
I had a question.
Yeah, right.
If you could go to the slide with your 3 scaffolds on it. Yeah, so I was wondering if you had any chemical intuition for why the 3rd scaffold also functioned similarly to the first 2, in that sulfur, the 5-membered sulfur ring seems like it would be fairly different from your.
So these scaffolds up to this point have only been characterized using in silico studies. So we can see here, this is the overall docking model for the actual protein. And using this modeling software like Molecular Operating Environment, we can look at, on the actual amino acid level, what makes ARD-150 work, and the actual different amino acids that it interacts with in that pocket. And so, so far, a lot of the synthetic effort has actually focused on scaffolds 1 and 2. We haven't gotten around to scaffold 3 quite yet, just because it's a slightly more expensive starting material. But based on that iterative process of using further in silico study to optimize those key interactions, scaffold 3 was one of the ones that worked. So we're interested to continue with synthetic and characterization efforts and see if that one can also be one that shows up as more potent as one already has.
So Wyatt, do you think that is one of the areas that looks very promising for this research?
So I would have to say, like if we're going to take this research, moving forward, what are the avenues for improvement? We want to get the full set of compounds characterized. And once we have that library and we can get an idea of which ones were more important and which ones weren't, using a structure-based study, we can go ahead and continue this process to iteratively improve over time and eventually hopefully create a treatment that can be used in medicinal applications.
Thank
Nice.
you.
Thank
we
you.
have another question, and I will be short, but we have to take this question. It's from the Q&A, okay? Do you know what cancer cell lines express higher levels of ARID4B? It could be more effective in tumor cell types that contain upregulated levels of this protein.
Mm-hmm. So the cell lines that we used for the actual the assays
was NCF7, which is a breast cancer cell line. But ARID4B itself has been implicated in increasing endocrine resistance. So this would be most heavily targeted towards cell lines that do show increased expression of endocrine resistance, as this is where it's going to have the most profound impact.
Okay, thank you very much, Wyatt, and good luck for your research with your research.
Well, thank you.
Evie, we can go to the next presentation, I believe, right? Just to be in time. We have Andrew who will present his work. Welcome, Andrew.
Hello.
Hi.
So, all right, so I'm Andrew Smith, and I've been working on a project called Developing a Neural Network for Dihedral Dependent Energies. So this is a computational chemistry project, and that mostly means that we're looking at these methods of reducing the amount of experimentation by specifically targeting a chemical property. In this case, we're looking at molecular energies. Now, these would traditionally be calculated for molecules using density functional theory, which is a fairly slow method, and that often takes hours or days and sometimes even weeks for larger systems. Now, some people have already begun working on this problem of how can we make that faster. One group is Smith et al. At Los Alamos, who has developed a neural network called ANI, which can rapidly do these calculations. However, there's a slight problem with this in that this model was only made for systems containing about less than 50 atoms and systems lacking extended pi conjugation. Now, for this project, we have to understand a couple of key terms about neural networks. And that's, on its most basic level, a neural network features works similarly to curve minimization, except with a incomprehensibly complex multidimensional surface representing the model's error. And we can see in the figure down here that there are a few different cases for where the model can end up. So ideally, it goes to the green circle here, which is the global minima. However, if it ends up on a plateau, which is the pink surface, it can end up having a very hard time progressing at all, which is why we have something called a learning rate. In this case, that was 1 × 10⁵. And if the model can't improve more than that, that means it's either in the pink circle at a plateau or in the yellow circle at a local minima. And that means that the overall accuracy will have a very hard time improving. Now, we also used an epoch-based training system. That means that our data was split into training and testing, and then that training was split again. And 1 epoch represents the amount of time it takes for it to see all of the training data. And then we also used active learning, which consists of how can we figure out sort of where on the error space is the model, what is it really struggling with? We're going to add more of that to the training data, which is going to force the model to learn and give it more intuition into that part of the error surface. Now, for the implementation, we had trained this model on about almost 5,000 density functional theory calculations with a learning rate of 1 × 10⁵ for a maximum of 2,500 epochs, and used root mean squared error as a loss function. And after about 1,600 epochs, it reached a root mean squared error of 30 kilocalories per mole. Now, 30 kilocalories per mole is actually not particularly good for an in silico method like this. But we did get a lot of interesting insights from the data. For instance, the data exhibited extremely high skew, as we can see in the lower left figure, with a whole 6% of the data being an outlier by a definition of 1.5 times the interquartile range. And so this meant that almost all of the data, as we can see in the right-hand figure, was actually having an absolute error of less than 50 kilocalories per mole. But a few data points had errors as high as 800 or over 1,000 kilocalories per mole. We also observed an interesting phenomenon with data normalization. So when we took the already published model for ANI, rather than the one that we were working on training, and we renormalized the predictions about the minimum energy predicted, it dramatically brought down that model's error from about 95 heart rate, which is one heart rate is 630 kilocalories per mole approximately. And it brought down that error to only about 6 kilocalories per mole. Yet this improvement in accuracy didn't propagate to our model. And some of the interesting other insights we obtained from this is that the absolute errors didn't display any correlation with the molecular size. And this is very interesting, as that was one of the chief things we expected. And we can see in this figure that some of the highest error species actually had relatively small size of less than about 50 atoms. And this leads us to believe that the primary cause of some of these larger errors are going to be, as we can see in the molecular images here, these top images being ones that perform very poorly on, and the bottom ones being ones that perform better on. Extended pi conjugation is having a really large effect here, as well as steric effects and geometrical effects that can affect that pi conjugation could be having a large effect on these errors. So going forward, we're going to attempt to implement some of the things we've learned by training this model, which was trained from a normally distributed sequence of weights and biases. And that's going to be, we're going to train using the already published model that exhibited a lower error, but we're going to focus on some of the things we learned from the active learning data from this model. And that does have some difficulty though, because the already published model only exhibits useful data and otherwise exhibits far too high loss to be useful in training when you can normalize at about the lowest energy. And that's not possible when the molecular geometry, which demonstrates the lowest energy, is in the testing split of the data rather than the training split. And this is an ongoing issue that we're working on right now, and we're working with some of the original people who published this at Los Alamos. And what we, although this is a current issue, we're very confident that we're going to be able to, with more training data, reduce the errors in this model to hopefully well below 1 kilocalorie per mole. Yeah, and that is all. Thank you for your time.
Thank you for this presentation, Andrew. Thank you very much. Let's see, any questions?
Nice presentation, Andrew. So I'm just curious, how did you get involved in this particular type of research?
Well, when I initially went to talk to Dr. Visco about being interested in doing some work at his lab, this was a project that had been, some very preliminary work had been looked at by a student who was actually leaving the lab to change what their PhD was going to be in. And I had some previous background in machine learning, and I'm a chemistry student. And so this was something that seemed very interesting, especially because of really just how extraordinarily long some of these DFT calculations take. Some for the training took about 2 weeks. And that is on UK's supercomputer cluster. So they're really quite long calculations. And so it's a very interesting project, I thought.
So to follow up with that, do you plan to continue this research with him?
Yeah, so this is something that is ongoing, and I'm going to continue to have some involvement on this project over the summer and into the fall, depending on the time scale it takes to reduce some of these errors. But yes.
Sure. Well, nicely done. Thank you.
Andrew, I have a question. Beyond all these calculations and, you know, a lot of work, machine learning and everything, can you talk a little bit about the practical applications that you see?
Yeah, so
of your work?
Yeah, so there's actually a very interesting end goal for this. That so the Visco labs that I've been working with to do this does a lot of work with organic photovoltaics. So hopefully the next generation of solar panels. And one of the key interesting factors here is, although the already published ANI model does a really great job on a lot of systems, there's some doubt as to its ability to really handle these systems with extended pi conjugation and that are larger. And both of those are key characteristics for compounds that are going to be interesting for organic photovoltaics. So ideally, we would like to be able to use this. So, right, once you do a DFT, all these DFT energy calculations, you would use that as an input to a molecular dynamics simulation. And that's going to tell you about the optical properties of a compound. So how it's going to interact with light and those types, and all these interesting things that are key for how good a solar panel could giving you a glimmer of, is this a good material for a photovoltaic? And that is the sort of end goal for this research.
Okay, thank you. Any other questions? Yeah.
I've got a quick question. If you want to go back to your first slide, this might be a little more technical, but looking at the actual way that the neural network approaches this learning model, I know that it has this learning rate where, if it hits a plateau and it does not move enough, then you're assuming that there's some form of error and it needs to be adjusted. How does the model differentiate between hitting a plateau versus hitting like a global minimum? Is it just the magnitude of the value that it settles on, or is there some other work there?
Yeah, so it is essentially the magnitude of the value. And it is a really hard question. It's essentially left up to the researcher's judgment of, do we believe that this model can actually be pushed to lower error? Or have we actually reached something that is, it really can't get any better than this? Another technique you can do to figure out whether or not you're on a plateau, although it's very time consuming, is you can lower the learning rate, right? So if you lower the learning rate enough and you're on a plateau, theoretically, eventually you'll get off the plateau. But again, it really is about the magnitude of these errors and whether or not the individual person believes it's a plateau.
Happy with the answer, Wyatt?
Yeah, that's great. Yeah.
Okay. Good. Thank you very much. Any other questions, or we're going to stop our, yeah, I think Evie, we're.
Yeah, I think just give
Nobody
it one. Yeah, I don't think so. I would just like to say thank you to everyone for presenting today. Great presentations. The last 3 days have just been phenomenal. You all should be very proud of the work you're doing. And we can't thank the faculty mentors enough, right? Because you guys wouldn't be where you are without them.
Yes.
For sure. So I hope you all have a great rest of your semester. You don't have much left. And I hope you have a really good summer. And Godspeed to each one of you.
And I would like to say also thank you to all of you. Congratulations for all of you for your great work. And I know it's hard and challenging. And I wish you good luck in your career, whether it's in research or in another direction. Thank you.
And thank you for moderating this.
And thank you, Evie.
All right, another year in the books.
Yep. Better, hopefully.
I know. Hopefully next year we'll be able to do in person. I won't be here, but yeah, I'm retiring.
Congratulations, anyway.
Thank you. Yeah, today's actually my last day.
Oh, well, it's a good day anyway.
It's a good day
for the end of yeah.
What's that, Wyatt?
What a way to end.
I know. I said, what a way for my journey at UK to end. I've been here 21 years. And yeah, I love the showcase. It's always like the big culminating event for our students. And I've been with undergraduate research for since day one when it started in 2004. So it's with bittersweet emotions that I leave today, but it's time to turn the reins over. And but I will miss my students. That's the one job that I loved. And with the reorganization of undergraduate research, they put the advising into the colleges, and that was my main job. So, I decided to take an early retirement. So, yeah, but it's bittersweet today. but good luck to each of you. And, you know, maybe our paths will cross again one day.
Well, thank you
Yeah,
very
for
much
sure.
for all the
Thank you.
effort in getting this to run.
Absolutely. Absolutely. All righty. Well, you all take care.
You too, Evie. Thank you very much. Thank you all.
Absolutely.
Bye.